Autonomous driving is a great promise of huge public safety and social efficiency benefits, okay? However, our automated mobility solutions must be provably safe and economically scalable to deliver on that promise, both against safety and economical scaling. Misdirected approaches to the problem may slow or even altogether risk the societal acceptance of these solutions. And that starts with the way that these solutions provide safety assurances to the public, communicated through the policymakers, regulators, and the economical scalability of this solution. If to describe shortly, the safety assurances approach, the approach to deliver safety assurances of these solutions bases on empirical analysis of these vehicles on the road. Whereas for many aspects, this is an impractical approach because, first of all, the closed loop nature of an automated driving. Once you insert any change, you're going to have to recollect data to prove your empirical safety. And, of course, the safety confidence goals that the society dictates in a way, or will dictate in order to accept autonomous driving solutions, are going to be very, very strict. So altogether, we're looking at a huge, possibly intractable empirical validation method. As for economical scalability, we see a rush to be very, very quick to market that brings in several brute force design factors into these solutions. Very aggressive designs in terms of compute power, in terms of how the mapping, which we will discuss later, is produced, and some very, very utopian assumptions about sensors requirements. And we will show how the two things link, how by solving and providing a formal model-based safety assurance, we can unleash a more graceful solution in terms of economical scalability. So the following slides will maybe a quick comment on the last bit. We have run into a case, a very clearly depicted case, where the onboard compute power requirements actually drained the battery to a level that the business case of that vehicle is no longer valid. To that very, very simplistic extent, the current approaches are risking the scalability of this solution, making the vehicle drive around 40% of what it could otherwise drive. So the next few slides, 2 or 3 slides, are going to be without videos and a bit laying out the foundations, and then we'll go for the fun part. So please bear with me. It just lays out the foundation. What we see here is tackling the challenges of safety and scalability when we talk about the environment sensing and the decision-making of that vehicle. We need to both make these modules safe and make sure that these modules scale gracefully economically. We will present a formal safety model for the decision-making layer. That's number 1 on the slide. We will then draw some understandings about what are sensing errors that are defined as safety critical versus sensing errors that are defined as simple comfort issues. And out of that, we can then move to number 3 and unleash a very, very interesting concept that we will share with you on how to architect the solution. So the responsibility-sensitive safety model means that it captures the very intuitive concept that full 100% safety cannot be guaranteed. 100% safety guaranteed only if we formally define what is the liability of that agent. Okay? So the formal model bases on this definition of what is blame and how we capture it very rigorously. Then, and let's run through the red lines here, we then propose and prove that by applying a certain very simple constraint, very simple check of the decision-making module, temporally local, meaning something that looks only on the very near term of that decision-making process, we achieve RSS, responsibility, sensitive safety, all the way into the future. And let's not go through the technicality of it. It bases on a definition of an emergency procedure, what is a safe state, and what is a cautious command. But at the end of the day, we have a very tractable, runtime efficient solution that can verify any decision-making module to be RSS safe, responsibility sensitive safe. Okay? Safe up to blame. And that is a key of this work. In order to now just to go to the last technical slide here that captures how do we classify sensing errors then. If we know what sensing errors could lead to a safety issue, we are clustering these very well disambiguated from any other sensing errors that apply to the comfort of the vehicle. And this distinction is the key for making a system very scalable. As long as you are taking care of the cautious part of things, separately from how you're dealing with the comfortable part of things, you can do many more things much more scalably. It gives a very formal and very stable model of dealing with this key concern of vehicle safety. So here we see the driving policy, our driving policy is trained with this formal safety model to negotiate this double lane merge situation very successfully. The two important figures here are 0 accidents over 100K runs and running time of 1 millisecond on a quite modest compute unit. So this is exactly what we wanted to deliver. I'll rush through this part with your permission and to demonstrate that we also scaled this model to deal with occlusions, potential occlusions. The cautiousness check takes into account vehicles that may be hiding a road user. And you can see that the agents that were trained by reinforcement learning are taking good care of slowing down or moving away from parked vehicles. Now, zooming out from solving the policy safety and the sensing safety issues, we're looking at how do we build a scalable perception system. We have to take into account, or this is another intuitive concept. As humans, you're using your eyes to get full understanding of the environment ahead of you. You can drive by your eyes. And we use the camera, therefore, as the base sensing solution for automated driving. Sorry, guys. We need to capture 4 elements of the environment model: drivable area boundaries, driving path geometry, movable obstacles or road users, and semantics. Semantics is a very broad family of things. Could be very explicit, could be the color of the traffic light, could be the fact that a pedestrian is looking at his phone. Now, to complement, camera will not deliver a autonomous driving alone. We need to deal with multi-sensor environment perception and how we harness this separately for safety and comfort of the drive. So as we said, camera covers all issues. However, for improving and robustifying, and these are 2 things, improving is comfort, robustifying is safety. Improving and robustifying the sensing, we may use radars and lidars for obstacles around us, and we may only use maps for the road geometry. This is something that no other sensor other than a visual sensor can deal with. And a map is the only parallel source of information for that. So Mobileye have devised a very economically aware, lightweight crowdsourcing approach where we're utilizing single camera vehicles, ADAS vehicles, to harvest information about semantically meaningful information, that's important, about the environment around us. What is the lane geometry? What are the landmarks around us? Transmitting 10 kilobytes per kilometer. We took it as a very important challenge to keep it very low bandwidth, not to depend heavily on communication. We then aggregate these snippets of information into a coherent map. And you can see we can deal with very complicated geometries. And lastly, we need to be able to use that map. That means that any autonomous driving vehicle should be able to localize itself within the map. And that's the purpose of these landmarks. And what you see on the left is projecting the map to the image space. It's not real-time sensing. It's how the map can really substitute the real-time sensing if something happens. That's the very nice result on the left. These lines that you see are coming from the map on the image. We can see that the localization endures hard weather conditions. Let's really run out. I'll skip also this part. An interesting piece of information is that in order to cover this orange area that you see effectively, if you want to cover it once a day, you need around 1,000 vehicles traveling around. And this information comes from a partner that has this dispersion patterns information. And if you want to cover it every hour, you would need around 15,000 vehicles spread around. That's not an intractable figure for this area that has millions of vehicles in it. A very small percentage of the vehicles. And lastly, we're blending the computer vision solution with our map in a way, and this is very important, that preserves the semantic accuracy. What is a semantic accuracy versus kinematic accuracy? Semantic accuracy is exactly the accuracy you guys as drivers use when you drive the car. You need to know which car is closer than which car, and which car is within each lane, and where approximately is it located within the lane. You have no sense of the kinematics. You have no sense of the distance or the relative speed. We're not claiming that this information is not needed for safety purposes, but for comfort purposes, which are a much broader part of the autonomous driving requirements base, you can deal with semantic accuracy. So what you see here is essentially, and I'll play it again, all camera-based. The map was built by a camera, and the vehicles are detected by a camera, so we can produce a three-dimensional model of the environment that preserves the semantic accuracy. It describes the environment as accurately as you guys would in order to drive within it. This slide only explains again that when we come to fusion, I have 2 more slides, so that's the last bit of it. The very important message here is that after we have gone through the toll of defining what is formal safety model for the vehicle and what needs to be done to assure it, and then we drew an understanding of what are safety critical sensing errors, we can completely decouple the design of the system, both in terms of sensing and both in terms of driving decisions. We decouple the areas that are in charge of the vehicle safety from the areas that are in charge of the vehicle comfort. And you can understand how directly that contributes to the scalability. If you can take care of the driving comfort without being worried whether you have influences of safety, you have a much more agile and much more engaged development process running. And you can relax dramatically a lot of the requirements on the sensing. We further show that if you do that in a sensor fusion setup, you can benefit from reducing the amount of data that you need for empirical validation of the sensing by square root. Let's take a figure, and it's a nice figure that the society already determined. The chances for a wing of a plane to fall off are 1 to 10 to the 9 hours, 1 to billion hours. And that's a kind of a figure we're looking for fatalities of autonomous driving. That's the goal. As we want to validate our sensing system to this extent, we can only use 10 to the 5 hours rather than 10 to the 9 hours using this approach of using the cautiousness check separately from different sources of information. So to conclude, this is the less safety responsible part of making the drive as comfort as possible, where we are blending map, camera, LiDAR sensors, radar sensors, all into the bundle. Just to finish this, we have seen all of this, and this is the paper, public paper that was published by our research team, by Professor Shashua and Professor Shai Shalev-Schwartz and their research team that presents this formal discussion. we do want this discussion, and we are already promoting it in front of regulatory bodies and policymakers to really formalize the discussion of safety of autonomous driving to make sure that we're not causing a delay in its scaling. That's all I had for you.